Hello. In this video, I would like to share with you how to use a formula to compute the probabilities within a binomial distribution. Many applications of probability and statistics are concerned with the repetition of an experiment. We call each repetition a trial, and we are particularly interested in cases in which the experiment, or each trial, has only two possible outcomes. Here are three examples. When repeatedly flipping a coin, the possible outcomes are heads or tails. When repeatedly rolling dice, the results could be seen as even or odd, or perhaps equal to a target or not equal to a target. If selecting cards from a deck and returning those cards each time, possible outcomes could be seen as red cards or black cards, or perhaps face card or not face card. When repeated trials of an experiment meet the following criteria, they are known as Bernoulli trials. The first condition is that each trial has only two possible outcomes, often called success or failure. The second condition is that each trial is independent of one another. The success or failure of one trial does not affect the others. The final condition is that the probability of success remains the same from trial to trial. The probabilities of success in a series of Bernoulli trials follow the binomial distribution. And you should recall from a previous lesson that a probability distribution is a listing of the possible values and corresponding probabilities of a discrete random variable, or a formula for the probabilities. To compute the probability of success in a binomial distribution, we use the following formula rather than a list of probabilities. The parameters are defined as follows. N is the number of trials. X is the number of successes among n trials. P is the probability of success in any one trial. And Q is the probability of failure in any one trial. Let's try a couple of examples. Example 1. If we repeatedly toss a fair coin, then in the long run it will come up heads about half of the time. But what's the probability that such a coin will come up heads exactly half the time in 10 tosses? This scenario does appear to represent Bernoulli trials. Each trial has only two outcomes, heads or tails. The trials are independent. Each flip will not affect another. And the probability for success will remain constant throughout the experiment, 50%. The number of trials is 10. And the number of successes we hope to achieve is 5. The probability of success is 0.5, or 50%, and the probability for failure is also 0.5. For future reference, the probability for failure is just 1 minus the probability for success. Now that we have the parameter values, we can evaluate the equation. Remember, the factorial notation means to multiply the integer value by each integer value smaller than it. And there you have it. The probability that a fair coin will land heads up exactly 5 out of 10 tries. If we were to flip a coin 10 times, or a group of 10 coins several times in a row, then we would expect 5 heads within the group to occur this often. Example 2. If we repeatedly roll a fair 6-sided die, in the long run it will come up 4 about 1/6 of the time. What is the probability that such a die will come up 4 exactly twice in 6 rolls? This experiment again describes a series of Bernoulli trials. Each trial has only 2 outcomes, 4 or not 4. The trials are independent. Each roll will not affect any other. The probability for success will remain constant throughout the experiment, 1/6. Please pause the video now and identify the 4 parameters needed for our probability function. The number of trials is 6, and the number of successes is 2. The probability of success each time is 1/6, and the probability of failure is 5/6. Now we can evaluate the equation. Please pause the video now to do so, and resume playback in a moment to check your work. If we were to roll a die 6 times, or 6 dice at once, we would expect to see 2 4s in the group this often. Not all experiments follow a binomial distribution, but many experiments can be designed to do so since the method for computing the probability of success is so straightforward. In future lessons, we will see how other probability distributions are utilized. Until then, I encourage you to develop your own experiments so that they can be tested with Bernoulli trials. Then compare your theoretical results by performing the experiment to obtain the experimental probabilities. Good luck.